Hello everyone. The topic for today's presentation is towards real-time scan versus BIM, methods, applications, and challenges. I would be presenting this on the behalf of the first author, Marcus Wallbaum. Before going into the presentation, we would like to acknowledge the support from the Center for Systems Engineering and Innovation at Imperial College, the Alan Turing Institute, and the Innovate UK. In today's presentation, we would cover the motivation for the study, a brief introduction to Scan versus BIM, the possible applications that we could achieve with real-time Scan versus BIM, the methods for Scan versus BIM, the challenges, and finally, the conclusion. We have seen how pandemic has changed the construction sector and how it accelerates the adoption of digital technologies. When we think about managing construction remotely, we need lots and lots of real-time data that is required to improve productivity, improve safety, and manage construction effectively. Further, we have seen in the past that a lot of devices are coming with different technologies to collect point cloud data or with 3D scanning capabilities that can be effectively used to manage the construction and collect real-time data. Further, there has been considerable progress in edge computing as well as cloud-based computing, in addition to a lot of construction robotics, which enables scanning of the construction site remotely. Although it comes with its own challenges, in the future we would see a lot of such devices being deployed in construction sites. So the question is, how can we effectively make use of all these technologies to manage construction effectively? And our focus here is to look at how can we do real-time scan versus BIM to actually manage construction better. So what is scan versus BIM? Scan versus BIM is a process of generating an as-built or as-is BIM by comparing an existing as-planned BIM to as-built or as-is point cloud data, which is obtained by simultaneous location and mapping devices, laser scans directly, or from 3D reconstruction from photographs. So what we do here is we look at the point clouds that is obtained from these technologies and compare it with them to create a building information model. So we are not essentially creating the geometry alone, but instead comparing to create insights. So we could do a lot of applications with this Scan versus BIM, which we would discuss in the next slide. One of the most common applications for Scan versus BIM is to compute progress monitoring. From the point cloud data, we could get what is happening at the construction site, then it could be compared with the building information model to understand what components are behind schedule, what are in schedule, and what are ahead of schedule. Another main application of Scan versus BIM is to identify quality and safety problems. So from the Scan versus BIM, we could get a point cloud of the current as is construction, and we could run rule checking, or we could look at the same from a point of quality to see whether everything has been constructed according to the design specifications. One of the newer application of Scan versus BIM is on robotic navigation as well as indoor localization for augmented reality application. Here, the point cloud is compared with a building information model to determine where the augmented reality device or the robot is, and then using the building information model to plan a path towards the particular area that the robot or the person in augmented reality should reach. These are some of the few applications of Scan versus BIM. However, the potential is limitless. For these applications to work, we need to have specific Scan versus BIM workflow. A typical Scan versus BIM workflow is as follows. First, we get the data using a 3D scanning hardware like LiDAR or SLAM devices. Then we pre-process the data so that it would be easier for interpretation. Then we interpret the data by comparing it with the building information model and creating insight. And this insight is used for the decision support application, such as progress monitoring, navigation, quality inspections, etc. Now we will go into detail on each of these. Data acquisition methods in the context of scan versus BIM could be classified as triangulation based methods or time of flight based methods. And it may also be classified as passive methods or active methods. The active methods, such as the time of flight based methods, use light or radio wave emitter to register distances to or outlines of an object, while passive methods like triangulation work with reflected light waves of the respective objects. The triangulation-based methods use at least two different vantage points to gather information, while the time-of-flight methods require only one vantage point. Therefore, time-of-flight-based methods could be described as outward sensing, while triangulation-based methods are inherently inward sensing. The data pre-processing can be classified into three categories: noise filtering, point cloud registration, and pre-segmentation. 3D sense data is often noisy and contains outliers and noise, something like sensor or registration artifacts. Triangulation methods in particular are prone to registration artifacts. For effective scan versus BIM, we need to remove these noise and outliers. However, implementation of clutter removal as a pre-processing is only possible if it makes sense to remove it if it can be clearly identified. However, most often that may not be the case. Secondly, since the point cloud data from the data acquisition devices is represented in a local coordinate frame, it needs to be then aligned with other scans and converted into a global coordinate system, and then aligned with the building information model. This process is called 3D registration and has been explored in the context of computer graphics and vision for robotics. Basically, it is performed in two steps. First, 3D pose estimation or course registration, and then fine alignment. After this, we need to do pre-segmentation. The main goal of pre-segmentation is to derive spatial semantic information from the pre-processed point cloud data. These include plane and subspace extraction, 3D reconstruction, object detection, and semantic segmentation. The goal of this step is to acquire as detailed as a spatial understanding of the sense environment, which would be then used for scan versus BIM. Now we will go on to the main methods for scan versus BIM. The first method for scan versus BIM is a point proximity based method. Here, regular comparison between sample point cloud data from CAD models and sense data from laser scans are compared. As design point clouds are sampled from performing virtual scans from multiple locations within the building information model. To achieve this, the building information model is registered in the scanner's spherical coordinate system. Then each sample point is expected to have a sense counterpart with exact same altitude and azimuth. A manual heuristic is then used to filter the points outside of the narrow range around the sample point. Then these point clouds are compared. Another way is the deviation measurement. A uniformly sampled point cloud from an as-designed BIM and a downsampled sense point cloud are converted into voxel-based representation and registered in the same coordinate system using a custom column-based registration technique. The comparison of as-designed and as-built state to detect and visualize deviation is thus converted into a trivial voxel grid comparison task. The second method is the surface coverage-based method to estimate scan versus BIM. Here, the points which are sensed are projected onto BIM surfaces to estimate coverage. The presence of points within a 3D outline of a specific BIM element is checked to understand whether that particular element exists or not. This approach depends heavily on domain-specific knowledge injection and resulting heuristics. If points can only be observed on some sides of the object, the main BIM representation is scaled down along the main direction of construction. Since this process is performed iteratively, the number of necessary scaling transformation determines the percentage of that particular element present in the sensed point cloud. The third kind of method uses machine learning based classifiers to detect objects and use it to compare with the BIM model. Here, 2D images are registered with 3D BIM data and subsequently back project the BIM semantic information, that is instance segmentation, onto the image planes to enable the application of 2D object recognition techniques. This is then used to compare with the 3D model to determine progress or other features. Now that we have seen different Scan versus BIM workflows and Scan versus BIM methods, the question remains, can it be directly applied to real-time Scan versus BIM? That's what we are going to explore now. During the real-time registration, the conventional ICP cannot be used as it has higher complexity. Therefore, an initial manual or visual alignment of scanner and BIM, that is known origin pose for the scan, would actually simplify the registration, and it needs to be performed. Further, indoor real-time localization approaches from BIM data, which was initially developed for scan planning, could be leveraged to ease the real-time registration. For point matching, pose estimation, and model alignment, the point matching algorithms that are generally used cannot be extended to real time because the azimuth and elevation angle of a point in relation to original point position cannot be extracted from the output of a indoor mapping system. Instead, an internal intermediary representation should be used from which a point cloud in the standard exchange format is generated during the post-processing. Uh, Therefore, in the point to object matching problem, a task of finding the closest point to point or point to plane real-time methods need to be developed for registration. Also, deep learning methods such as lightweight single-shot object detection models that employ 2D object recognition readily lend themselves to extensions for real-time performance, as many mature real-time 2D object recognition methods are available, and these could be applied directly. With measurement accuracy between 1 to 5 centimeter for mobile mapping systems, real-time Scan-vs-BIM approaches are required to handle significantly more deviation between the as-designed and as-built geometries. Further, the horizontal and vertical scan resolution for indoor mapping devices can differ dramatically depending on the device's rotation axis, and therefore the variation in point cloud density needs to be considered in real-time Scan-vs-BIM. Further, built environment contains large-scale, featureless, repetitive, and not distinguishable objects. Therefore, the current point cloud Scan-vs-BIM approaches cannot be easily extendable for real-time performance, as the real-time methods needs to perform data association between point cloud and 3D BIM representation within a short time. Applying novel 3D object detection, pose estimation, and model alignment approaches within the computer vision community to single object Scan versus BIM problems seems promising. However, these have not been tested on small sets of small scale objects. But the kind of like large scale featureless repetitive objects in building information models, there might be problems that might come when we are trying to apply these methods. As conclusion, we now have seen the applications that real-time Scan versus BIM can have for construction, especially in this pandemic situation. However, the existing methods cannot be directly used, and we have suggested some methods for improving the real-time performance. We have also identified the limitation of existing methods for Scan versus BIM with respect to their performance. Therefore, there needs to be much more research in the domain of real-time Scan versus BIM for it to be widely applied in construction. And it would be really beneficial for the newer technologies such as augmented reality, robotic data acquisition methods, etc. With that, The floor is now open for questions. Thank you.